Going to explain in this tutorial how we're going to use Comsol to analyze a problem that has two different types of physics that are kind of coupled together. So it is kind of the first example of what we call multiphysics. And the physics we will study will be explored using a simple design of a bus bar. So if you look on the screen here, you see that the bus bar is basically a bracket, and this bracket is something that is used to conduct electricity right here, and it can carry current in it, and it will act as a resistor essentially. If we have something like a voltage on the bus bar, then it will act like a wire. So let's say that the bus bar will have this bolt here. So it's a bracket. The bracket is going to be made of copper, so we'll choose copper material for it. And then we have three bolts. One bolt in this region, and two other bolts on the other side of the bracket. And then the bolts are made of titanium alloy, which is different from brass. So that titanium has different conductivity from the brass. And what we have in this model is that we're going to have a voltage on the top bolt of 20 millivolt. This is a very small voltage. And then we're going to ground the two bolts on the bottom. So if we think about it as a circuit problem, there's going to be a current that will flow from the top bolt through the brass, which is like a wire, and it will kind of flow into these two holes. However, this is a large body, and the current gonna flow everywhere, so there will be some passages in the body or in the bracket, and we need to look at the distribution of the current within the bracket. As the current is flowing here, it will cause Joule heating. And the Joule heating, as we know from our courses on electricity, is the power that is produced when the current flows in a resistor. If we remember, it is I squared R, or I times V. And that's kind of the power is like a heat source, and then the heat is going to be everywhere distributed. So we have a heat source coming from the electromagnetics. The electromagnetics is basically the electricity problem that we have. So the heat source is going to come from there, and it will start pumping heat inside this bracket, and the bracket is going to be cooled by air. So it's going to be air cooling the surface, air cooling the surface, and from the bottom we also have cooling. The only places where we're not going to have cooling would be around the bolts, because they're bolted and the air cannot get inside. So this is kind of a description of the problem, and I'm going to go over steps in Comsol on how to do the modeling for this particular problem. So let's pop Comsol here and have a look at basically the starting with the model. So we have here a 3D, so it's going to be a 3D model, and then we can actually proceed with the next step is going to be selection of the physics, and the physics that we have, we will choose Joule heating. And we can add with the add sign, or we can just click on the arrow to the next step, and it's automatically is going to add the Joule heating physics. And then we would like to define the study, and in this study we're going to do just not transient but a steady state solution for the equations of the current and the equation of the temperature. So we will have two equations, one for the current, like basically a Kirchhoff law, but for a distributed system, and the other one is for the temperature, which is the Fourier law that's similar to Kirchhoff's law, and the two together are solved on the mesh. So we're going to choose stationary, and then that will basically define what the model is going to be. Now we have two options, either to create the geometry ourselves, and we will come to that in another tutorial, or to import the geometry from an existing library. And there is actually a model library. If we go to now we are clicking on the geometry, and we can look for something that has a bus bar. And in the model library for Comsol, there is a Comsol Multiphysics node, and then AC/DC analysis mode, like for node for electric type problems and chemistry and so forth. So we're going to look at the multiphysics because this problem combines two different types of physics. And we look here at the bus bar geometry. If we click on it, it will show us the bus bar, and we can either open the model and the PDF that describes it, or just a model. So let's say we're going to open the model itself, and then we will kind of import that model, and it's already opening the model for us, and is going to bring in the geometry, and from the geometry we should be able now to proceed and describe the process of the design. As you can see here on the screen, it popped the bus bar geometry, which has a bracket and 3 bolts. So this is already done. So the first aspect of this, the additional node that we have to, or subnode in the model that we have to always be cognizant of, is materials. So we have to add materials. So if we go to the node of the materials, then we right click, then we can add material, or we can choose it from the browser. Alternatively, I can go directly to the material browser, and I look for built-in materials, because copper and titanium are very common, so we will find them. So if we look here, we see copper is right there, and then we click add. Then it will take a little time to bring in the copper properties that are relevant with the problem, and all of the other properties are in the library. So you'll see that things like Young's modulus, Poisson's ratio, these things are required for mechanics, so they are not clicked with green. The things that are required for heat transfer and electricity or electromagnetics are highlighted in green. So electrical conductivity, heat capacity, relative permittivity, density, thermal conductivity. So all of these are already there, so we're happy with the copper. And it did apply all of this to all domains. Okay, so now if I click on any domain, 1, 2, you can see domain 1 is the bracket, and then domain 2 would be something like on the back here, for this is domain 2, and domain 3 you find it on the top bolt, and so on. So these are the domains that we have. This is domain 2 here, and I can always go back to the reference configuration by clicking on the icon with the 3 Cartesian coordinate system here, the default view. Okay, so but I don't really want everything to be copper, so I want to just add I want to have just domain 1 to be copper and everything else to be made of titanium. So I'm going to go and 2, and then click shift and go all the way down to 7, and then subtract those. Like if I just subtract, then it will take them out, and then I have now applied my material as copper only on domain 1, which is the bracket. Okay, so now I'm not still clear because there's 3 bolts that are not defined. So I have to go to materials again and open the material browser. And by the way, you note that if you don't introduce the material, you're gonna get an error. So you can see here, maybe if the resolution is good enough, then under materials there is a red cross here that shows that we have something undefined. So it reminds you that we have to go back and then define it. So if we go into the library again, we find that we have a titanium beta alloy, and we will choose this as our second material. And at this point I don't have anything defined. So it says manual. Then the best way, since there's so many domains related to the bolts, the best way that I see is that I'm going to have it defined for all domains. And then subtract the domain that represents copper. So I'm going to go to instead of manual, I say all domains, and then I go to domain 1 and then subtract that one. So now I define domain 2, 3, 4, 5, 6, 7 as domains that have the titanium material, and then the copper, if I go back, is only domain 1. So my system is material is well defined, and I have no issue with that. Now I go to the physics. Next step. So the next step is the subnode for the physics and try to figure out what's going on there. First is I check on the defaults. So I have a whole bunch of defaults there under Joule heating. So the first one is Joule heating model 1, and it applies to all domains, and it needs the conductivity, electrical conductivity, and it needs the permittivity, and it needs thermal conductivity, and it needs the density, it needs the specific heat. So all of these, it says from material. It means that Comsol now has recognized that it has these values, and those values are going to come from the library that I already selected. So I'm okay here. And the other thing is that so I can actually contract this, and I don't really worry about it at this point. And then I need to figure out what are the equations that represent this system. So I have a physical understanding. As I mentioned, we're solving simply 2 problems together. One is like Kirchhoff's law, that the current is equal to the difference of voltage divided by the resistance. And the other one is that the Fourier law, which means that the heat flux is proportional to the difference in temperatures divided by distance. This is the Fourier law. So these 2, when I look at them in a differential equation form, exactly what I said here, you will see that this line here, the divergence of J is equal to Q. This means that the derivative of the current J, the use J, is the same as I in circuit theory, but J is per unit area. So the divergence of J means the derivative of J is equal to whatever surface charge that we have. And then J is proportional to E. Sigma is the conductivity, which is the inverse of resistivity. So this line here is like just Kirchhoff's law of current is equal to the voltage divided by the resistance plus an additional electromagnetic term for transient, so we'll forget about that one. And then the electric field is minus the gradient of the potential or the voltage. Gradient means derivative, so the electric field is like the slope of the line, if you will, that defines the distribution of the voltage. So we have a voltage here is 20 millivolts going down to 0. Ground is right here. So it's going to be, there's going to be kind of a decreasing from 20 all the way to 0. So you're going to have a gradient, and the gradient is going to cause an electric field here. And then the equation that represents the temperature, this is like energy equation, conservation of energy, and the solution to this, you have the gradients of the temperature, and the derivative of that must be balanced by the heat source. And the heat source Q is actually the Joule heating that we are talking about, the I squared R. And that comes from coupling with the electric equation for electric current conduction. So that's basically the idea behind these two equations. The top one is underlined and the bottom one is underlined, and then the two in between are just kind of relationships that take you from one to the other one. So now we have understood the equation. Then we go to the next one to look at the electric heat source, and the heat source, the equation for the heat source, it shows that the Q, the heat source, is equal to J times E, which is like the current times the voltage, okay, in circuit theory. I times V is like the rate, the heating rate, or the power that is produced. So we're okay on the heat source. This is a default. And we now look at the boundary conditions. So we have boundary conditions. First, if we look at electric insulation, we have boundary conditions that come default. That everything, all of the boundaries here are electrically insulated. Meaning, what is the meaning? You can see the meaning in the equation. That n dot j, n is the normal vector to the surface, times the current, J is the current, is equal to 0. It means that there's no current coming out of the surface. That means it's insulated. So that's kind of, all of the boundaries come to be insulated here, electrically insulated, until we override that. And then if we look at thermal insulation, is very similar. The equation for it is shown here, that the normal vector n times the heat flux is K gradient of T, is equal to 0. It means that there's no heat flux coming out. So the current is like the heat flux. So we have two things, the current and the heat flux, and both of them are set to be 0 by default. Now when we cool this bracket, we're going to have to override this condition for the heat flux, that we want the heat to come out. We don't want to have to be thermally insulated. So we will come there and introduce a boundary condition that will define the heat flux that goes out. So I have to go to Joule heating, and then if I right click, then it should show me a menu, and the menu has both heat transfer and electric currents, because this is the coupling between the two. So the heat transfer part, I would like to add a heat flux, because I want to get the heat out of the surfaces. So I have heat flux, and the heat flux, now I go to investigate. It doesn't have any domains, and I have the heat flux condition. It gives me two options: either general inward heat flux. If I am adding heat flux into the bracket, it will heat it some more, so I don't need to do that. But I would like to have the air cools the surfaces. So that is controlled by this condition. It's called inward heat flux. Inward or outward depends on the difference between the surface temperature, T, and the external temperature, like the air temperature. So the difference between the surface temperature, the Comsol will calculate T, and then if I give it an air temperature T external as 293.15, that's the room temperature, then that difference will determine whether the heat is going to flow in or out. So, and how fast it's going to flow is going to be controlled by this heat transfer coefficient, which I can input here in units of watts per meter squared K. So I can put in any number. Usually it's a low number like 100 or so, but I'm going to also include an idea, and this idea is how to input such parameters using a table. So we're going to try to define some of these parameters in a table in the global definitions in a few minutes. And that number is already in the table, so I'm going to write it HTC. That's the name of the parameter that I have. And therefore, if it exists, then Comsol is going to take that number and use it. If it doesn't exist in the global definitions, then I'm in trouble because it wouldn't know what HTC is. So let's go and check on the global definitions. And the global definitions is already parameters that defined, and those you can define them by yourself. So they were already defined. L is the length of the bracket. So if you change that, then the bracket can go smaller or bigger. Radius 1 is the radius of the bolts. So you can here is 6 millimeter, but if you type 9 for instead of 6, then the bolts are gonna, and rerun this, then the bolts are gonna get bigger. So it's a very useful thing to have instead of numbers, you have initial numbers, but then you can call them parameters over there, and they're defined as parameters in the geometry, and they control the geometry. So TBB is the thickness of the bracket of the bus bar, and W is the width of the bus bar. You can make it wide or small. So let's say if I want to make it wide, instead of 5 centimeters, I can just change it here to, let's say, 10 centimeters. So if it's 10 centimeters, then I have to do the geometry, and you'll see that it will change. There are two, so if you look for L, radius 1, TBB, WBB, and MH is the size of the mesh, as we will learn in the next tutorial. We can control the mesh size. Is given as 6 millimeter here. Then all of these are geometry parameters, control what the geometry is. Then we're going to add 2 physics parameters. One is the heat transfer coefficient, is given here as 5, and then the other one is the voltage that's applied to one of the bolts, and here is given as 20. So let's go to geometry to kind of see what's happening here. And then since I changed the width to 10, let me build it just to make sure that it actually went through the change. And you can see right away that it did actually go through the change and made it a wider bus bar. Okay, so now I defined the heat flux. So I was just kind of having a diversion that I defined the heat flux, and the heat flux is defined on but it doesn't know what domain it will be defined on. So what I would like to do is define it on all domains, all boundaries will be cooled, except for where the bolts are going to be fastened. And to figure out where the bolts are going to be fastened, then I come to this surface here, and then if I right click, then it will take it out. If I go to this surface, right click, it will take it out, and then the surface also right click, it will take it out. So these 3 surfaces will not be cooled by air and will revert back to the default condition of thermal insulation. So I have now defined the heat flux that will be kind of taken out of that system, and it's all defined. So now I can go ahead and solve the heat transfer problem, the combined problem, but I'm not going to get any results because I haven't defined what are the boundary conditions for the voltage, because the voltage is going to have to be applied so that it will create the current, and the current is going to create the heat, and the heat is going to create the temperatures and the distribution. So I have to go back to Joule heating and redefine, or not redefine, but define the boundary conditions for the for the electromagnetic problem, which is the voltage. So let me just see if I can have this figure to be within our range here. Just reduce the size a little bit so we can see it. Yeah. So we are back in to look at the model, and then we go to Joule heating, and then we want to go. Now we don't want heat transfer. We want now to switch to the electric part. So if we look at the electric part, you can see that I have electric currents instead of heat transfer. So the electric currents here, it will give me options for the boundaries. What do I want to do in the boundaries? In fact, what I would like to do is two things. What I'd like to do is apply 20 millivolt on one bolt, and then I would like to apply ground on the other two. So let's say that I want to have electric potential, which is potential means voltage, and then define where that is. And what I'd like to do is define that the potential is going to be on this surface. So I added 32, and the potential that's applied is VTOT, because this is a parameter that I already defined as 20 millivolt in my table of parameters. And we are done with this. Now I would like to do the other two bolts to have a ground before I run this case. So I'm going to have to go back to Joule heating and then select, right click and select again electric currents, and then in this case I can say ground. So in this ground is going to add another node, and the node is empty, no domains. Then what I'll do is I'm going to go to this domain, this domain here, and then right click 19, this domain, and right click 12, and that will define ground conditions for me. And then I'm pretty much at the point where I can run the case. I'm not going to talk about the mesh at this point. We will leave this for next time. But we are essentially ready to go to study, and then right click and then compute. The calculations now is going to go through combining the heat transfer and the distribution of the temperatures. They're going to show up somehow, and then also we should be able to see the distribution of the potential or the voltage and the distribution of the current if we want to. So there's a lot of rich information that can be shown in here, and we should be able to, we're gonna try to run this case, and then once it is completed, then we will be able to go back in the next tutorial and analyze the results and see what they mean, and also look at the methods of displaying the different results, how we're going to adjust the range of conditions for the temperature. We will see that some of the conditions are going to be reasonable. Like, okay, so we're done here for the calculation in front of your eyes, and you can see that the temperatures are pretty high, 620 to 624, because the bracket I changed actually from the original dimension, so it's a pretty hefty one, so it had a lot of heating, so it's basically a bad design. I have to kind of control the temperature, otherwise it will burn something. And you can see that the temperature contours here. So before I leave this, and I'll come back to it, I can go to the results section, temperature, surface, which is basically what you see here. When you click on surface, it shows you the tab that shows the settings for the graph. So we just play just a small game that if you look at the range is already defined automatically. But if I don't like the color here because it doesn't really show a very nice distribution, I can go to have manual color range, and instead of it starts minimum at 619 degrees, goes to 624. but maybe I want to get more distribution. Then I can reduce the maximum to, let's say, 622, for example, or 21, and then replot. So you can see now you get more resolution for a certain region that are within this range. If you go to 622 and then you replot, then you get more resolution in that range. If you go to 30, for example, then the range is very big. Then you can't see much variation. So you will be able to control the variation if you control that range within the plot. So I'm going to basically stop here, and then we'll continue giving another tutorial just to finish up this multiphysics model for the Busbar.